So we understood that torque of a force F about a point O is given as R cross F, where R is the position of the point P where you are applying the force with respect to any reference point. For the sake of simplicity, the pivot. This is R vector. And angle between R vector and F vector is theta. Fortunately, we have, if you take this as phi, sin phi is equal to sin theta, because sin theta is equal to sin 180 minus theta. Where R is the position vector of the point of application of the force with respect to the reference point. Let us take some conceptual example. When I apply the force here, what is the torque? What is R? R is 0. Torque about the point O. Torque about this point O of this force F when it passes through the reference point will produce 0 torque because R is 0. This gives us the concept that when the force or line of action passes through the reference point O, when the force F passes through the reference point O, its torque about O is 0. No turning effect. It's quite evident practically. If you ask a baby to open the door, he will go and push it at any point, not at the axis. And by the instinct, baby can understand that the door can be easily rotated or opened or closed when we push it or pull it at furthest point. Therefore, the baby by his instinct will push the door at the edge. He doesn't know physics, but practically, physically, by instinct he can understand that, oh, the door can be easily, most easily rotated, most easily opened, or most easily it can be closed when he will push it or pull it perpendicular to the plane of the door, and furthest apart from the axis, furthest from the axis, he will have to push it or pull it, making his angle, making the angle of his force or angle of his hand 90 degree. When he pulls or pushes the door normal or perpendicular to its plane, the door can be easily rotated, opened or closed. Who? The baby can understand, even though he is ignorant about physics. So by instinct, a baby can also understand that the turning or the twisting effect of the force in physics is decided by three quantities. How much force you are applying, number one. Where you are applying the force, number two. In which direction you are applying the force, number three. All these three things as a whole will decide whether the body will rotate or not, or is getting twisted or not. The twisting effect or the rotational effect or the turning effect of a body is not simply the force. All these three parameters, three effects, along with the magnitude of the force, the direction of the force, and the point of application of the force will take care of the turning effect of the body. It can be zero, it can be non-zero, it can be maximum. The maximum turning effect you are getting when we apply the force at the furthest apart, at the tip of the pen. When you apply the force, there is the pivot. To have the maximum twisting effect, we should apply the force at the furthest apart, at the tip of the pen. And as much as possible, you have to push it or pull it. And always you have to make the finger or the line of application of the force normal to the pen. So theta should be 90 degree. The force should be as much as possible. And the point where you are applying the force, that point of application of the force should be as far as possible from the pivot. Then only you can rotate the pivot with most effective way or in easiest manner. That ease of rotation or the turning effect is known as the torque. Torque is governed by the three quantities, and when you are applying the force through the point or at the point, you cannot, when you apply the force here, you cannot rotate it because R is 0. This is based upon the purely practical matter. Okay, let us take another example. This rod is hanging. You are applying the force here, you are applying the force here. This is say R, or you can take it as a midpoint. This is L. You are applying the force perpendicular to the rod and applying the force of same magnitude. Find the torque of this force about O in first case, about O in the second case. In the first case, the torque is equal to how much? R. This is R cross F. R cross F. R cross F. In which sense? In anticlockwise sense or outward. It rotates in anticlockwise sense when you apply the force here. How much? RF sin 90 degree. That's equal to R is equal to L by 2 F. This is the torque or twisting effect of the force about this point in first case. In second case, you are applying the force of same magnitude in same direction, but the point of application of the force is further. You are applying the force at the double distance. Here R is equal to 2L. So tau equal to RF sin 90 degree. Here R is different, here R is different. Let it be R1, this is R2 suppose. This is L into F. Which sense? Anticlockwise. So here the ease of rotation is twice the ease of rotation here. The twisting effect or the turning effect of the force here is double the torque of the force at this point. Torque of the force acting at this point with respect to this point is double that of the torque of the same force acting at this point with respect to this point. Therefore, torque 2 is equal to torque 1. Double turning effect at this point. Turning effect of this force when I apply the force here is tau at O in second case. Turning effect of the force which is applied here with respect to this point is tau about the suffix point O in the first case. This torque is tau 1, or if you don't like this term, you write tau 1. If you don't like this term, you write tau 2. It's tau 1 and this is tau 2. And tau 2 is equal to twice of tau 1. When you apply the force here, apply the same force here. Here it is, you are having some easiness. Here also you are having some easiness, but this is 2 times easier than this case. This means that angular acceleration here will be twice angular acceleration of the rod when you are applying the force here will be twice the angular acceleration of the same force applied at this point. So the turning effect of the force in this case is twice the turning effect of the same force when it is acting at this point. Totally practical thing. Well, so from this example 1 and example 2, these 2 examples, you can understand that the torque depends upon the reference point. With respect to different reference point, the torque will be different, and also torque depends upon the angle theta. It also depends upon the point of application of the force. When you apply the force at this point, no torque is produced. In the example number 1, it is cleared. And when you are applying the same force at 2 different points, the ease of rotation or the torque will be different about same point O. Let us take another example. I apply force. I apply a force here. I take the same rod. I apply the force. I apply another force of same magnitude in opposite direction. I need to calculate the torque of these 2 forces. About this point. 2 questions. Same rod. Here one force, here one force. Here one force, here one force. These 2 forces are equal forces. These 2 forces are negative forces, equal in magnitude, opposite in direction. Well, and this is the reference point, this is L. Let it be L dash. Let it be L dash. This is L. This force will produce a rotational effect about this in this sense. Let it be tau 1. This force will produce a rotational effect about this point in this sense, this tau 2. The net rotational effect can be written as tau 1 plus. Because of this force about this point, the rotational effect is, this is R1 cross F. In which sense? Clockwise. R1 F clockwise plus, and angle is 90 degree, need not worry. Sin theta is 1 plus, due to this force about this point, this is R2 into F, the anticlockwise sense. So you are getting R1 plus R2 into F in clockwise sense. What is R1? R1 is equal to L plus L dash. What is R2? That is L dash into F. So it is 2L dash plus L into F. Either you can write anticlockwise in clockwise sense, or you can write this is in, or you can write, if this is x direction, this is y direction, this will be what? Minus k cap direction. Either this is correct, this is also correct, this is also correct. So what do we have calculated? Find the torque. Find the net torque about O. Now come to this question. This force is applied here. With respect to this is R1. R1 cross F. R1 cross F. This is R1, this is F. R1 cross F. This produces a clockwise twist, and this force produces an anti-clockwise twist. And two torques are added factorially. The net torque equal to T1 plus tau 1 plus tau 2, and tau 1 is equal to R1 F anticlockwise minus KF. I choose rectangular coordinate system, and tau 2 is equal to R2F in which direction? Plus KF direction. So this is R1 minus R2 into F. Since the angles are angles between the radius, the position vector and the force vector is 90 degree, sin 90 is 1. But R1 minus R2 is how much? L. Answer. The net torque is in positive z direction or out or anti-clockwise manner. This is correct, this is also correct, this is also correct. So this gives us the idea that when you take two equal and opposite forces, the net torque does not depend upon the reference point. The net torque produced by two equal and opposite forces does not depend on the reference point. Because this is a constant quantity. L is a constant quantity, F is a constant quantity, and K cap is a constant quantity. So this type of force, this type of forces or couple of forces. If it is plus F, this will be minus F. Therefore, these two forces are called couple of forces, and the torque produced by this couple of forces is called couple. A couple or the net torque produced by two equal and opposite forces doesn't depend upon the reference point or reference frame. A couple does not depend upon any reference frame. With respect to all the points of the universe, the torque produced by two equal and opposite forces will be same for all the points, all the reference points. This is a great concept. And from this example, what you understood? The torque produced by two equal forces depends upon L dash, where exactly you have kept the reference point. The torque here depends upon the reference point. Here torque doesn't depend upon the reference points. Except this case, except the forces will be equal and opposite. For all the cases, all other cases, the net torque about any point or the torque about any point due to a single force or the group of forces depends upon the reference point. Only one condition is that when these two forces are equal and opposite, then the torque produced by these two about any reference point in the universe will remain same or remain equal or remain independent. And that particular torque, combined torque of these two forces is called couple. A couple doesn't depend upon any reference frame. So when you deal with a couple, one should not ask about which point, which reference point. In electrostatics, we have the electric dipole. Torque experienced by a dipole does not depend upon any reference point in a uniform electric field. Similarly, in magnetics, torque experienced by a magnet doesn't depend upon the reference point when it is kept in a uniform magnetic field. Therefore, torque experienced by an electric dipole or magnetic dipole when placed in a uniform electric or magnetic field doesn't depend upon any reference point. And that is based upon this concept of couple derived from the mechanics of rotation. Well, the torque about a point O, let us take the coordinates of this point be 1, 2 and 3, and you are applying the force. F is equal to I cap minus j cap plus 2k cap Newton. These are all in MCAS unit. At the point where you are applying the force has coordinates -2, 1, say -1. Question is, find the torque of the force F about the given point. The formula is Torque tau is equal to R cross F. What is R? R is the point the position vector of the point P where you are applying the force with respect to the reference point O, and R is equal to this position minus this position vector minus this position vector, or position vector of the point P minus position vector of the point O. You should not always think that the reference point is always at the origin. So, if you take the origin of the coordinate system, let it be O, let it be O dash, or you can write Q instead of O dash. This is RQ and this is RP. Always you should not think that this reference point about or with respect to or relative to which we can calculate or we are calculating the torque should be always present at the origin. It may not be the case for all times. Here it is not present at the origin because the coordinates are not 0, 0, 0. The origin coordinates are 0, 0, 0. 0, 0, 0 in MKS unit. Okay. Now, R is equal to RQ minus RP because R is equal to RP minus RQ in this case, because by triangle law of vectors, when we add this vector with this vector, you are getting this vector. The triangle law states that when any vector A representing one side of the triangle is added with the other vector B which represents the other side of the triangles in the same manner, the closing side taken in the reverse order. This order was clockwise. The closing side of the triangle is this, taken in which order? Reverse order. C represents this side, the closing side taken in the reverse order represents or will be equal to the vector sum of these two vectors, a resultant of these two vectors. Using this idea, we can write this vector RQ plus this vector R taken in the same order in clockwise sense must be equated with the closing side of the triangle taken in the reverse order is represented by this vector RP. So, RP is equal to RQ plus R. Therefore, R is equal to RP minus RQ, not RQ minus RP. Well, what is RP? Position vector of this point and coordinates are given minus 2 I cap plus j cap minus k cap. What is RQ? Its position vectors are 1. The coordinates are 1, 2 and 3. So, its position vector is I cap plus 2 j cap plus 3 k cap. Well, minus 2, minus 1, minus 3. Plus 1, minus 2, minus 1 j cap. Minus 1, minus 3, minus 4. You can check from here. minus 2, minus 1, minus 3. 1 minus 2, minus 1. Minus 1 minus 3 is minus 4. This is the R vector. Equation number 2. And the force vector is given how much? I cap minus j cap plus 2 k cap. Substitute R and F from equation 2 and 3 in equation 1. By using 1, 2 and 3. These 3 equations, we have tau is equal to minus 3 I cap, minus j cap, minus 4 k cap. This is R vector cross the force vector, that is I cap minus j cap plus 2 k cap. And to evaluate this cross product, either you can go directly by expanding these terms or expanding these brackets, or you can use the tabulated form, like in determinant form we have I cap, j cap and k cap. Then the components of the position vector are, these are minus 3, minus 1 and minus 4. Then the components of the force vector, plus 1, minus 1, plus 2. How much you are getting? You may know how to expand the determinant. Leave this column, leave this row, and start from left hand side to right hand side, from top to bottom. Minus 1 into plus 2. Then from the bottom to the top in reverse order or reverse way. Minus 1 into minus 4. I cap minus j cap. You leave this column, leave this row, and again you start from left to right, from top to bottom in this way, then in this way. Minus 3 into plus 2 minus plus 1 into minus 4. It's not plus j cap, it's minus j cap. Then only you can follow the order from left to right, from top to bottom, then plus k cap. For this, the third row you leave, the third column, it's not row, third column you leave, and this first row you leave, and follow the same order. Minus 3 into minus 1, from top to bottom, from left to right, minus plus 1 into minus 1. This is k cap. Evaluate. This is minus 2, minus 2 minus, minus 1 is plus, plus 4. I cap minus, minus 3 into plus 2, minus 6 minus into minus plus, plus 4 j cap plus k cap minus into minus plus 3 minus 1 into plus 1, this minus and minus plus. So you are getting minus 6 I cap is minus 2 into minus 1 plus 2 j cap 3 plus 1 4 k cap. This is the torque, and the unit of torque is Newton meter, because it is the product of a distance and the force. Unit of distance is meter, unit of force is Newton. So the unit of the torque will be Newton meter in MKS unit. Answer. Now let us understand the significance of this term, and this term. In general, if you want to write, you can write the reference point has the coordinates r1 or x1, x2, x1, y1 and z1. And this point P, where you are applying the force for which you are calculating the torque about this point Q. Let it be x2, y2 and z2. Then the R will be equal to Rp minus Rq, and you will be getting x2 minus x1 I cap plus y2 minus y1 j cap plus z2 minus z1 k cap. And this force, let it be fx I cap plus fy j cap plus fz k cap. Fx, fy, fz are the components of the force along x, y and z axis. Here fx is plus 1, here fy is minus 1, here fz is plus 2. Then you have to cross multiply these two vectors r and f, and you are getting something into I cap plus something into j cap plus something into k cap. That something you will be getting after tabulation, and we can call this something into I cap, that's something into j cap, that's something into k cap as the projection of the torque or the component of the torque about or along x axis, y axis and z axis respectively.